Okay, welcome back everybody to the EOCP's conference 2021. Couple little reminders. There is a survey that would be beneficial for all of us if you fill out at the end of the day 1 and day 2. There will be some prizes as well for those people that participate in the surveying, so keep that in mind. You're in the wastewater treatment stream. We're starting this afternoon with the science of pipe cleaning. Our guest speaker for now is Kenneth Billingham. He works with KEG Technologies. That's a long acronym. Ken is the international product specialist with KEG. It's a German manufacturing of highly efficient pipe cleaning tools and camera systems. The KEG Technology Inc. in North America distributor for these products. His responsibilities include customer and reseller support for all of Canada, Australia, New Zealand, as well as the Pacific Northwest of the United States. Many years of experience and knowledge in its diverse collection systems throughout the area help him find solutions for the challenges faced by today's users. So without ado, we're going to pass it over to Ken.
Thank you. Thank you very much. Thanks again to the EOCP for inviting me to speak here today, and thank you all for attending. Quick note, if you have any questions or comments or something you would like clarification on as we're going through the presentation, then by all means, don't be afraid to bring the question to the table, and it'll on the chat, and it'll be forwarded to me, and then we can respond and see what's there. Keep in mind, if you have a question, there's likely others who have much the same question, so we'll try and answer them as we go along. There will be a question and answer period at the end, time allowing, but that's the goal as we speak now. When we're ready, can we put the presentation up? Okay, folks, so this is the science of pipe cleaning. I am Ken Billingham, and you are here to maybe get a little bit of help and assistance in where we're going with all of this. So again, it's today is the day, so we're going to do it. Here, what we're going to look at. I'm not advancing, guys. Oh, there we go. Thank you much. Okay, well, we're going to look at it we're going to look at it from a multiple point of view. From the crew's point of view, we're trying to find ways to have them work a little cleaner, a little smarter, maybe get the job done with not quite so much sweat and toil, and letting the equipment actually do the work. When you're managing a department or a company that does this kind of stuff, of course, budgets are always an issue, and manpower. How do you get enough people? Where do you get enough equipment from? How do I get around and do all this stuff? And hopefully we can provide a few answers for today. And then last but not least, as a business owner, if we're in business doing this stuff, our goal is to make a profit, be responsible to our shareholders or to the owners of the company. And if we're doing that, then how do we manage to keep the work level high, the quality of work high, but reduce things like costs and things along those lines? And again, we hope to be able to provide some answers today. What we're looking for is solutions to some of these problems, and maybe a bunch of others too. And again, the questions will come on the floor. And what I'm suggesting we're going to do is that we're going to talk about nozzles, nozzle design, as well as the way that we clean pipes, and challenging the issue as to whether or not we're doing everything in the best possible manner to get the job done. So what we hope to do here, some of the benefits we're going to talk about, is we're going to be able to clean your wastewater and storm lines better. By better, I mean more efficiently, possibly quicker, get more of the debris out of them in a manner, helping to reduce things like fuel costs. And typically we can help folks save between 9 to 17%. But even if we only present a 5% decrease in fuel costs, it's still a substantial amount of money. Reduce man hours, machine hours for cleaning lines. Again, if it takes an all day to run and clean 1,000 feet of pipe, if I can get 1,500 feet done in that same day, well, it's a better day and it's more productive. That's all. It's all said and good. Wear and tear on the equipment. This piece of equipment are expensive to buy and expensive to operate and maintain. And if we can find ways of reducing those costs, maybe not quite be such a high demand on the equipment, that's always a benefit to people. It makes the equipment last longer and makes the maintenance and repair costs come down. And then, of course, conserving water to clean lines. Most municipalities use potable or drinking water. to clean the lines, money, water that's been bought and paid for, and quite often, if we can reduce those numbers, that is a benefit to the municipality. The Tier 3 nozzles, although they tend to be the more higher priced product on the marketplace, they are, at the end of the day, the lowest cost option after you look at the whole operating cost and everything else. Our company is a company that manufactures all levels of nozzles, from the most simple basic nozzles to some very efficient, very well designed. And it depends on the market as to what you are looking for. Clean pipes, that's job one. If at the end of the day we're not doing the job, we're not getting the pipes clean, then we have to shake our head and scratch our ears and say, why are we not doing this better? But before we get into all that, of course, let's go back and talk about some basics. I'm going to lay some groundwork here. The idea is to offer some basic thoughts and everything so that, the understanding is there and we can move forward into the rest of the presentation. So if you'll allow me to, we're going to talk about the positive displacement volumetric water pump, or the water pump if you prefer. Hose reels and hoses, always important. How much hose I have on the truck, how long is the hose, and things along those lines. And then the next item up, of course, would be the pressure gauge. And we're going to have a discussion on that in a little bit, and you might be a little bit surprised by some of the comments I'll make in regarding to how that provides information to the operator. And last but not least, we'll look at nozzles. I know that my manufacturer builds nozzles, and I specialize in supplying and providing the tools to do the job. But I left this to last because until we get all the other basics lined up and talked about, there's not much sense in talking about nozzle design or the way we use the tools. So as we look at the pump, I call it again a positive displacement volumetric water pump. There are many manufacturers of pumps who will make all kinds of comments and claims about their design is better than the other guys. I don't get into that discussion. As long as the pump can provide the flow and maintain the pressure, then I'm happy with the result. I can live with that and I can work with that. You notice how I mentioned the pump provides flow. It does not create pressure. The pressure comes from the back pressure or from the nozzle or from the restrictions in the line that cause the pressure to come up. So again, the pump provides the water, the system provides the pressure as we go. The main reason why we have these pumps on board the trucks, it takes the mechanical energy from the vehicle or from the jetter trailer or from whatever it is I'm using and turns it into hydraulic energy. So I've gone from mechanical energy to hydraulic energy so I can use it and send it down the hose. We talk about hose reels, and we talk about diameters of pipe and a hose and stuff like that. Many different configurations and many schools of thought onto what's the best system to have, and it's all dependent on what you as the contractor, municipality, utility need the tool to do, and we can look at different designs. The main purpose or the reason for that hose being there is to take that hydraulic energy that we developed at the truck and move it down the length of the hose to where the job site is, whether that's 500 feet away, 1,000 feet away, or whatever. We can go from there. When we look at sewer cleaning hose, again, different configurations. Here I have a chart that looks at hoses from 1/2 inch to 1.5 inches in diameter. It talks about the typical maximum operating pressures. Again, this is not cast in stone, but this is the typical of what you see in industry. And I've highlighted the 1-inch hose in yellow because that's what I'm going to use most of the time for my discussions and points of interest. If you look at it, you'll see that the chart talks about the minimum flow in the 1-inch hose anywhere from 30 gallons to a maximum flow of 80 gallons, which is what it's designed for. You can run a little less, you can run a little more, but this is a design criteria of the hose. In the numbers, like if you look at 80 gallons a minute, you'll see in brackets next to it the number 1.1. This number indicates the pressure loss per foot of hose. So what I'm showing you here is at 80 gallons a minute in a 1-inch hose, I will lose 1.1 pound of pressure per foot of hose, or 110 pounds of pressure over 100 feet of hose. And again, 600 feet would take me into 650, 675 pressure loss. Of note is the fact that if we look at the other end of the 1-inch hose at 30 gallons, you'll see that the pressure loss is now stated as 0.16. So what this is showing us is that if we can reduce the flow, our pressure loss diminishes, and at the end of the day, it's about maintaining pressure at the end of the hose and providing or delivering that pressure to do the scouring and cleaning we want to do. So again, we can go as high as 80 and beyond. I've run as much as 90, even as much as 100 gallons through a 1-inch hose, but the pressure loss starts to become quite substantial. Just to reiterate again and talk about the same thing in a different manner, in a hose, or in the hose, we consider flow versus pressure. In the hose, the more flow that I try and push through a specific diameter of hose, the lower the pressure will be at the end of the hose. So if I can drop the flow down or lower the flow, I gain an advantage in having more pressure. And I'm going to have some examples coming up here in a second, but just to reiterate, I have a lot of discussion with people who say, no, we need flow to clean the pipe. And the reality is the pressure of the water coming out of the nozzle is what's going to scour and clean. The flow will move the material. So if I have 30, 40, or 50 gallons a minute coming out of the hose, and I'm in an 8 or a 10 inch or a 200 to 250 millimeter sanitary line, I don't have to have a lot of water. As long as I break the material free and I have 30 or 40 gallons of additional water, I can make this stuff travel and move down the line. When I look at water pressure gauges, and I mentioned before we're going to talk about that, we just saw some slides that said basically, hey, wait a minute, you said I lose pressure as I go down the line, and if my truck is showing 2,000 psi, what can I expect to see at the end or down by the nozzle? And we're going to look at, again, I have some examples coming up. The main purpose of this pressure gauge is to provide the operator with some feedback so he has a target to work with. But the question or the big point to make here is that even though I have a pressure of, I'll use 2,000 psi at the truck, I don't have that pressure at the nozzle. So here what I've done is I've taken a comparison. We'll look at different flows coming out of the same hose. Everything is based on 600 feet of 1-inch hose and 2,000 psi as a starting pressure. Here I've jetted my nozzle for 80 gallons a minute, and I'm going to run it down in this configuration. What I look at the end of the hose, I have a pressure at the end of the hose of 1,327 psi. I've lost a little over 670 psi along the way, which is a little more than a third of the pressure I started with. And there's my pressure loss in yellow at 1.12 psi per foot, or my indication earlier was 1.1. So that's where that came from, and see what's there. What I want to look at here, or what I want to bring up to discussion here, is I have what I call FHP. FHP is fluid horsepower, and it is the unit of measure of how much energy is available to be put to work. And in this case, I'm looking at that at the end of the hose. So I take the flow, you see the formulas there as well, GPM times PSI divided by 1714. The flow and the pressure, and I've taken the pressure at the end of the hose, not the pressure at the truck. So I'm dealing with the 1327. I have 80 gallons a minute, divide by 1714, and I end up with a number that resembles 62 fluid horsepower. So I want you to keep that number in mind, that 62 fluid horsepower. It's kind of important as we look at things. I'm going to move forward, and now I've taken the same configuration, same hose and everything else, but I've rejetted the nozzle to 60 gallons a minute. So even though the truck is capable of delivering more, I'm only wanting to use 60 gallons a minute, 2,000 psi. Before I had an end pressure of 1,372 psi. Now I have a pressure of 1,621. I've come up almost 300 psi in pressure. Again, my comment earlier, pressure is what scours and cleans. So this will give me a nozzle that will have, or a tool that will have more scouring and cleaning capability, or more thrust and power to get this nozzle up the line than I would have in a nozzle that has a less pressure at the nozzle. Here I have a loss of pressure of 378, just shy of 380 psi, and I've lost 18% of the pressure generated versus almost a third, or just barely over a third from before. And again, in brackets, if you look at in yellow, you'll see that I have a 0.63 psi per linear foot of pressure loss. So I've dropped my pressure loss from 1.1 to just over 6, or 0.6 psi, a substantial drop again for an increase of pressure at the nozzle. Fluid horsepower ratings at this now, I've dropped the flow, so it's flow times pressure, but my pressure has come up. So my fluid horsepower rating at this setting is 57 fluid horsepower, which means that although I've dropped a bit, I've gained some advantage. I've taken my flow down by 20 gallons, and I've gained some advantage in pressure. I've lost a little bit of my fluid horsepower, but I can still provide a very good experience on cleaning. Here's a nozzle, same configuration, same truck. I've just changed the jetting in the nozzle, and I've taken the flow to 50 gallons instead of 60. Same 2,000 psi, 600 feet of 1-inch hose. Pressure at the end of the hose has risen again by a little over 100 psi. I'm at 1737 at the end of the hose, and I have a fluid horsepower rating, loss of 262, 0.43 psi per linear foot. Interesting note here is if I were running a 3/4 inch hose, my pressure loss per linear foot at 50 gallons is actually 1.8 psi per linear foot. So it's roughly 4 times a higher pressure loss on 3/4 inch hose with the same flow in it. My fluid horsepower rating here at the end of the 1-inch hose with the 50 gallon a minute is 51 fluid horsepower. Again, still very respectable, still able to put to work and do what I need to do, being cleaning and scouring and climbing the hills and doing the different things that I need this thing to do. And if I take it down to the extreme where the 1-inch hose is designed for 30 or 35 gallons a minute at the lower end, again, the same 2,000 psi, same 600 feet of 1-inch hose. The pressure at the end of the hose has risen now to 1,871 psi. I've only lost 128 psi or 0.21 psi per foot. So you can see the trend here. As I can lower the flow, I can increase the pressure. And if we accept the fact that pressure is what does the scouring, pressure helps with the propulsion and everything else, then it works very well. At the end of the day, it's about a correlation between flow and pressure and what's the right combination for the task at hand. So we'll get into this discussion a little bit later on. Fluid horsepower rating at 35 gallons is down to 39 fluid horsepower. It doesn't sound like much, but again, we're going to talk a little later about the efficiencies of the nozzles and how I can put this amount of power to work in a manner to clean what I need to do properly and efficiently. You'll see a lot of charts in my presentation. I'm not going to apologize for them because I think they help to clarify. What I'm looking at here is you can see my categories are a GPM or flow. By engine, I'm talking about how many horsepower the engine must provide to be able to deliver, in this case, 80 gallons. I need 104 horsepower. As a side note, in the bottom of the slide, you'll notice I marked that the engine horsepower requirement is calculated. I give the formula, and I give credit to where the formula came from a company called Myers Pumps. Myers has been around forever, and they're a bit of a real name in the industry. Fluid horsepower is calculated again the same formulas before, flow times pressure, divide by 1714. So back up to the chart, 80 gallons a minute, 104 horsepower required to get the 80 gallons a minute. The pressure at the end of the hose, based on the fact that I started at 2,000 psi with 600 feet of 1-inch hose, is at 1327. My fluid horsepower rating is 62, and I have a column there called 1,000 gallons. This will let you know basically to compare how quickly that truck or that jetter will go through 1,000 gallons of water. In this case, 12.5 minutes, and it's empty, and we have to go get more water. Here I look at a 60 gallon a minute configuration. Again, we saw that earlier. I've dropped the flow by 25%. My engine, the demand on the engine, or the requirement for horsepower, is dropped down to 70 from 104. I've dropped 33% in the engine demand. My pressure has gone up by 22%. My fluid horsepower rating has dropped by 8%, so I have a little bit of a loss there, but I have much of a gain looking back at the flow and the demand on the engine. And I've gained 36% run time on that same 1,000 gallons of water. And instead of 12.5 minutes, now I'm looking at 17 minutes. I go down the example. I talk 50 gallon a minute setups. I'm 38% less water than I was at 80 gallons. I'm 42% less demand on the engine or the truck to make this thing work. And got the pressure is up by 31. I'm down fluid horsepower by 18%. But look at my tank of water will now go from 12.5 and 17 all the way up to 20 minutes of runtime, which means I can get more work done, again, providing I have the right tools and I'm using the right methodology. Go down and look at the last bit of the chart here, 35 gallons a minute. I'm well below half the water consumption. I'm well below half the demand on the engine. I've got higher pressure than all the others. I'm down 37% in fluid horsepower, but I can get a full 30 minutes out of my tank of water at this flow rate. Actually, I'm going to back up for a second. The interesting talk about all of this is the fact that if that tank of water lasts longer, the operator can spend more time in the pipe cleaning and less time chasing water, which means that he can do more work at the end of the day, or more productive, profitable work at the end of the day than if he was out chasing water. Doesn't mean he's not busy. If he's chasing water, doing this and doing that, that's all part of the job. But if you can save him 1 or 2 or 3 trips for water in the day, it ends up being a lot when it comes to time in the pipe, making the pipe clean. So here we are talking about all kinds of power and everything else, and it all sounds great. It's like looking at these cars and say, boy, those things must really go. But until the power gets itself down to where it's going to hit the ground and where it's going to be used, it really is nothing. And until we can show a way to turn all of that energy, all of that power into useful work, we need to stop and look and see what we're doing. So unless you can get the power to where it can be used, it's of no use to anybody. And now the nozzle guy is finally going to start talking about nozzles. So we're, what, 15, 20 minutes into the presentation, and I'm there. When we talk about nozzles, you notice I spelt nozzles with a letter. The letter S is basically a $, and that reflects on the fact that nozzles can cost a fair bit of money. That reflects on the fact that if we have the right nozzles doing the right work, it's going to offer you an opportunity to get better quality work done at the end of the day without having to work the equipment or the crews harder. What the nozzle does, and because up until this point the water's been leaving the jetter and traveling down the hose to the work zone, now the nozzle will direct the water as needed, whether the jets are all in the back of the nozzle and set up to propel the nozzle, whether it's a rotary nozzle and some of the water will be used to spin and rotate the end, or whether it's a nozzle with forward jets and back jets for unclogging and opening up block lines. What the nozzle does, it pulls the sewer hose up the line, allowing the nozzle to get to where it's needed to do the job I need it to do. It takes the material that I'm trying to remove from the pipe, breaks it away from the walls or wherever it is, and gets it moving, getting it going back to the point of evacuation, which is typically either back at the truck or it's allowed to travel back to the treatment plant. Frontline soldier, rubber hits the road, there's a lot of terms I could use here, but it is the point of the spear. It's the pointy end of the spear when it comes to cleaning pipe. And as much as we love our trucks and as much as our crews have years of experience and have done this for months and months and months and years and years and years, this is the point of attack. And if we don't have a sharp tool or the proper tool at that point in time, then it can be a costly experiment. Selection and application of the correct nozzle will ensure a job well done and on budget. I'm not advocating a toolbox full of nozzles or other tools. What I'm saying to you is, depending on what the truck is designed or the jetter is designed to do or you need it to do, you need to have the correct tools to get that done, whether it's scouring, whether it's climbing hills, whether it's moving debris or whatever. And every configuration and every job basically makes a change, but there are a lot of commonalities. So NASCO is the National Association of Sewer Servicing Companies. They are an association in the United States that are dedicated to our industry. They represent not only municipalities and contractors who are the people using the equipment, but the vendors who provide the equipment, whether we're providing jetter trucks or sewer hose or nozzles or any other tools. NASCO is the place where we all come and sit down and talk and try and find ways to advance and better the industry and possibly find better answers to some of the questions out there. The purpose of well, I should back up a second. NASCO are the people who brought this tier designation to the industry so that people who were buying nozzles could determine, I need a nozzle for this kind of work and I'm going to be looking for a tier 2 or a tier 3 nozzle. and allow them to do some shopping based on those criteria. It also allows vendors like myself to represent our products and say, I have here a nozzle that is a Tier 3 design or a Tier 3 high efficiency design, or this is a Tier 1 design, and of course the pricing will reflect all of those changes. So it allows people to speak more openly and more directly as to what their equipment is able to do, and allows the people who are looking for equipment to express very clearly what it is they're trying to achieve. If we look at Tier 1 designs, again, the tiers work: Tier 1, Tier 2, and Tier 3. Tier 1 being the lowest, least efficient design, Tier 3 being the highest. So Tier 1 is the least efficient design, and it is 30% efficient. You'll see I've marked in red because I like to refer to this not as 30% efficiencies. I like to call this a 70% inefficient nozzle. One of the biggest advantages of this tool is it's priced right. It's dirt cheap, but it's obviously going to cost some money if you're going to operate it. When we talk of a Tier 2 nozzle, Tier 2 nozzles are designed to give us about a 55 to 60% efficiency rates, which again in red I've indicated is a 40 to 45% inefficient. If you had a vehicle that was running in this efficiency levels at 70% inefficient or 40-45% inefficient, you'd probably be looking at something a little less expensive to operate. Tier 3 nozzles are by definition required to meet a minimum of 80% efficiencies. So the Tier 3 design, if it's a true Tier 3, is going to be a minimum of 80% efficient, and there are manufacturers out there who have turned out some product that are up in the high 90s, 97, 98% efficient. These tools are the ones that are the priciest, but they're also the ones that deliver the most for the time that you have them, and go from there. So these are the ones we recommend, but we always have a conscious understanding of where we're going as far as costs and things like that. When we look at the different tiers, you'll see on the left hand of the screen, you'll see that tumbler, or that glass beaker. That's what that is. You'll see the glass beaker there. You can see where the water goes into it from the side, and then it causes turbulence inside the nozzle. And if you look at the picture of the nozzle next to it, it's a flat bottom, just like the bottom of that beaker. And when the water goes into that nozzle, it slams into that wall of steel. Literally, the flow stops for a microsecond, and then the next bit of water coming through tries to push it out the orifices. What this does, it creates turbulence inside the nozzle and actually stops the flow of water momentarily, but it does stop the flow of water. And what that does is it causes the loss of energy, because all of that turbulence inside of there is loss of energy. If I go back to my analogy before of those high-powered race cars, if you think about internal combustion engines or things along those lines, if you understand hydraulic systems, again, hydraulic in an excavator, things like that, they try and eliminate as much turbulence in there as possible to allow the clean flow of the liquids or the gas or whatever's coming through there to be as clean and as efficient as possible. We try and do the same thing with nozzles, and again, the choice of that nozzle will make a huge difference in the outcome, not only of how clean the pipe gets, but it will also make a huge difference in how quickly and how well I can clean that pipe, or how well that nozzle can travel, or how well that nozzle will carry material behind it. So again, the left-hand side of the screen is a Tier 1 or a Tier 2. They're made the exact same way inside. The differences we'll talk about in the next slide. On a Tier 3 nozzle, Tier 3 requirements are quite simply that there's an 80% efficiency level minimum, and that there's a way to direct the water or divert the water, as you can see in this case, around the bowl. So the water goes in on the right-hand side in the blue arrows. As it hits the water, the green arrows swing around and goes from there. The velocity of the flow of water is barely impacted. The turbulence inside the nozzle can be reduced to almost non-existent. Case in point, we have 98% efficiencies in some of our nozzles. If you look at the photograph next to it on the right-hand side with the blue markings in it, you can see how we built our nozzles for Tier 3, and it's relative, and it shows how Tier 3 nozzles are supposed to be designed inside, so that the water gets inside the nozzle, gets turned around, there's no edges, there's no flat surfaces, everything comes and goes, and it goes right through. Tier 1 nozzles, quick and easy identification, because I told you before that Tier 1 and Tier 2 are built the exact same way inside. So if you look in the bottom of the nozzle where the hose connects, you might not quickly determine which tier nozzle I have. But a Tier 1 nozzle is very simple. Where the water comes out, or the jets or the inserts or the holes, they're drilled. There's nothing fancy about it. It's just a straight up chunk of metal. We've machined it. We drilled some holes into it. End of the game. In a 1-inch size, this will run you $250 to buy a brand spanking new nozzle. The downside is it's 30% efficient when it's brand new, and depending on how well the quality of the material is inside and how well the machining is done, that deteriorates rather quickly. The water running through those drilled orifices will quite quickly erode. A lesser, like carbon steel, it'll, excuse me, it will erode that very, very quickly, and once that hole starts to get misshapen, ovaled out, or enlarged, then the flow rates change, the turbulence inside the nozzle increases, and the efficiencies drop. So again, 30% is where it starts. Where it ends, it's always a good question. We talk about a Tier 2 nozzle, and here you can see the picture of a Tier 2. If you look at the picture, you can see quite clearly this nozzle has replaceable or threaded inserts inside. So the advantage of the Tier 2 nozzle, of course, is that I can replace the jets. I can up the efficiency because I have a better exit strategy coming out of the nozzle, which means that I can tune this nozzle to the job. I can renew this nozzle quite simply by changing jets inside of it and go from there. From a machining point of view, it's very similar to the other nozzle. We turn it in much the same manner, but where the big change comes in is that we are threading the orifices where the water comes out as opposed to just drilling it. And of course, those inserts that go in, they can run $40 to $50 each very quickly. And when we do those, of course, if you got 6 jets at $50 a piece, it's $300 plus the cost of the nozzle. So from $250, you're going to take this nozzle up to closer to $600 in purchase price. It is one of the best upgrades in the market, the cheapest upgrades in the market you can get into, and it works quite nicely. When we talk about Tier 3 nozzles, now they're the most expensive versions out there. I can supply you with a Tier 3 nozzle and help you spend $3,000 to $4,000 very, very quickly, which I'm sure everybody appreciates. But at the end of the day, it's what the tool will do for you. So we've got excellent fluid mechanics, and fluid mechanics in these nozzles is the term we use in the way the water gets turned and gets put and applied to the job. So it's got replaceable jets, it's got excellent fluid mechanics. The performance is as high as possible. Again, 98%, as much as 98% on board sometimes. Some of our Tier 3 nozzles and a lot of the Tier 3 nozzles in the marketplace are low 80s, but there are abilities to go. Typically when you're getting into these higher end nozzles, they use a better grade stainless steel. It's wear resistant, it lasts longer, it doesn't rust or all the other stuff. The machining that goes on these things is absolutely phenomenal. If you have a chance to look at it or visit the plant and everything, it is crazy just how precise this is. And again, the minimum requirement for Tier 3 is 80% efficient, and of course the top end is sky's the limit, but 98% is as close to perfection as we can get. Most cost-effective nozzle design. These nozzles tend to last long, they tend to work consistently, and they tend to provide good quality work and a job well done. Here's a pictogram, if you want, of some designs of Tier 3s. All of these nozzles shown are Tier 3s. I want to invite you to look at the 3 of them and just figure out which one is going to give you a better return. And keeping in mind, turbulence is the enemy, or is what you're trying to reduce. The first design is our design. It's a patented design that we have. The second and third both show Tier 3 nozzles that are good quality tools, and customers or people don't make mistakes by buying those other tools. But if you're going to get into this stuff, buying the better, well, you buy the best you can afford and just get the job done. Turbulence, again, being the factor. If you look on second and third photographs, you can see where there's some swirling going on or some turbulence going on inside the nozzle. Here's that diagram again of a nozzle with the water coming in the bottom end, hitting the top end, going through those channels, getting turned around, and going back out through the inserts. You'll notice here I pointed with an arrow to where the water is actually redirected and sent towards the rear of the nozzle. And then if you look here, we look at the inserts. These are engineered systems. You can't just match any insert on back of any nozzle and figure you're going to do things. We've done this, we've studied this, we've had universities involved, we have physicists and some very, very well-educated people in our company that have designed all of this and make this into a tool that really works well. Here's the inserts we're looking at. We use, or most people will tell you they use a ceramic insert, and the ceramic is there for one reason and one reason only. It is to reduce the erosion of the orifice as the water goes through. So the ceramic is very resistant to the water eroding the orifice and causing it to misshape or getting larger and everything else. The trouble with ceramic is it's quite fragile. Think of your coffee cup or your dinner plate. If it gets banged or receives a good shock, it's going to crack or break. And then once the insert cracks or breaks, then it's a throwaway and you need to get something new to replace it. So it's different manufacturers use different compounds to get this job done. We use a titanium ceramic compound. The ceramic for the erosion, the titanium for the resistance. So it works quite nicely. If you look at these photographs, you can see two different designs. The one on the left is a design that's quite common in industry. It's a larger funnel, very short barrel, and you'll see what happens as the water comes out the bottom end of the insert, it tends to want to fan or spray open. When you have an insert like the one on the right, what that does is it very short funnel, but a longer barrel, which forces the water into that barrel or that size for a longer time, which means that the water jet, when it comes out, stays intact for a longer travel, which means I get more propulsion, I get more thrust, I get better cleaning power out of the nozzle. Quick video we have to look at the different designs. On the left is a high efficiency 98% nozzle. On the right is one that is in the lower 80s design. I'm going to turn the video on and you'll see in the beginning we have a look at the water jets coming out of both. They look quite comparable. If you say to yourself, hey, you know what? Yeah, that other nozzle's not doing so bad. When we see what happens as the pressure comes up, because now we're running at idle, maybe under 1,000 psi, and once you bring the pressure up to 2 and 2,500 psi, you'll see what starts to happen on the jets. Keep in mind, the one on the right is the least efficient nozzle, the one on the left is the more efficient one. You can see what's happening here. This plume of water coming out of the right-hand side is starting to fan and open up, which means that that stream of water is not going to impact debris. It is not going to propel that nozzle as well as the nozzle on the left. Are we getting any questions up to this side? We have one. Okay, well, let the video finish and maybe we'll address that. Okay, what was the question?
We did have one question came in. Some of the audience members are looking at using these kinds of jets to clean struvite, magnesium ammonium phosphate out of pipes.
Yep.
And they're wondering if, I know you're kind of doing an overall education now.
Yeah, but to address that specific question, I won't get into detail on that, but yes, and we'll talk a little, you'll see some videos in a bit of different styles of nozzles that are intended for exactly that job. Struvite is quite hard and is difficult to remove. There are tools to get at it and do that. So if you're working in a treatment plant, you know what struvite's all about and you have had to deal with it. So a little later in the presentation we will have, and I will make sure I bring that up at the time and point it out. So again, high efficiency on the left-hand side, standard design on the right-hand side. We're back to my charts. No apologies on my part. Again, we're looking at flows. We're looking at engine requirements or engine horsepower requirements to get the flows we're after. We look at fluid horsepower ratings for each and every one of those flows. Again, everything based on 600 feet of 1-inch hose and a starting pressure of 2,000 psi. I try and make this as clear as possible. On a Tier 1 nozzle, which are 30% efficient, in the top level, the 80 gallon a minute column or row, whatever, line, if I have 62 fluid horsepower and I use 30% of it, then I'm using just a hair over 18 of that fluid horsepower putting it to work. And it goes down the line from there. Not a big difference between the 80 and the 50 or even down to the 35 gallons. But if I take a nozzle, a Tier 2 nozzle, and I literally double the efficiency of the nozzle, then the output from the nozzle will double alongside that. So I've gone from 18 to 37 and from 15 to 31 on the 50 gallon a minute side. Here's where it starts to get, I'll use the term very interesting. Here I'm looking at a Tier 3 nozzle. And if I look at a Tier 3 nozzle at 50 gallons a minute, it delivers 41 fluid horsepower, and this is a Tier 3 80%. This is just borderline Tier 3 nozzle. It delivers a fluid horsepower work output from the nozzle of 41 fluid horsepower as compared to an 80 gallon a minute Tier 2 nozzle, which only delivers 37. So at 50 gallons a minute with a Tier 3 nozzle, I can effectively clean as well as an 80 gallon a minute Tier 2 nozzle. The advantages, of course, you've seen the increase in flow times or run time and everything else. Now, if I take that Tier 3 design and go from the minimal 80 to the optimal 98% efficiencies, I can take a Tier 3 high efficiency nozzle, that's what the HE stands for, high efficiency nozzle, and that gives me an outflow of 38 fluid horsepower at 35 gallons, and that matches the Tier 2 at 80, and I've got less than half the water consumption, which means the tank's going to last for 30 minutes rather than 12 and a half, which means that the engine RPM is going to come down. The demand on the engine has gone from 104 horsepower required to 45. All of that represents savings in not only water and productivity and time increase spent in the pipe, but you're going to drop your engine RPMs, you're going to drop your fuel consumption, you're going to drop your demand mechanically on the vehicle. If I take and look at the different flows, and I use a Vactor pump, because the Vactor is the Vactor pump is a piston that moves back and forth, and every time that pump cycles, and what I call a cycle for a Vactor truck is full left hand and then back full right hand. In other words, a stroke out and a stroke back. That moves 5.5 gallons of water every time it goes through a cycle. So if I'm putting 80 gallons a minute out, that thing must run over 15 cycles in a minute to give me 80 gallons. At 50 gallons, it runs 9. And at 35, it runs just under 7. So at the end of 2 years, 3 years, 4 years, the wear and tear on that pump is dramatic. Or the lessening of wear and tear on that pump is quite dramatic. So put into a different aspect, we can say that if I run the truck at the same output, or the input to the nozzle from the truck is the same, I can get more cleaning and pulling power from a higher efficiency nozzle than I can from a lower efficiency nozzle. I can get over 3 times the power over a Tier 1 with a Tier 3, and I can go 1.5 times the power of a Tier 2. Keep these numbers in mind, because when I look at lowering, because remember where I showed earlier where the 50 gallon a minute matched the 80 in a Tier 2, and the 35 gallon a minute in high efficiency matched the Tier 2 and actually matched as well the Tier 3 at 80 gallons. By doing that and turning down the demand from the truck or the input into the nozzle, turning things down, I can maintain that level of cleaning and pulling power I was satisfied with. I can reduce my water consumption dramatically. Water consumption goes down, fuel consumption goes down. It's just there's a correlation, because it's all about RPMs, it's all about displacement of pistons and things like that, and the less demand I have on the engine, the more fuel I will save as we go on. Wear and tear on the vehicle, I just described how quickly things like that piston pump on the Vactor truck, from 15 to 9 down to 7 cycles, depending on what flow I'm running. Heat and noise will drop dramatically. In January, in some of the colder areas, the heat is very much appreciated. This last summer, I think it was the end of June, when we had that 46-degree days and everything else here in the Lower Mainland, yeah, nobody wanted the heat. It was crazy. And of course, increase in productivity. If that tank of water, instead of running 12 or 15 minutes, can now run 25 or 30 minutes, that means I fill up less often. If I fill up less often, I can stay longer in the pipe. More time in the pipe will translate quite simply to more pipe cleaned in a day and faster circuits around. Reducing flow, of course, there's benefits to this. The less water consumption means fewer fill-ups. We just talked about that, how that translates into more time in the pipe getting the job advanced. My pressure goes up. You saw that in the beginning. We talked about basics. As we drop the flow in a specific size hose, we drop the flow in the hose, the pressure at the end of the hose will increase accordingly. Probable fuel savings, the reason I put in probable is because there's no guarantee, obviously, but if we think about the logic behind this, if I've taken the engine, I can run the engine at 1,000 RPM rather than running it out at 15 and 1,600, anybody can easily gauge how much fuel saving that's going to be. Maintenance costs come down again if I'm not driving the machine to the ground. If I'm not pushing it to its limits, then I'm running it in the 50 or 60% range of what it's capable of. It's going to last longer. Safety environments go up. Folks, if the noise levels come down, and things like that happen, then the operators are more aware of their environment. Being aware of your environment is a key role to being in a safe situation. You can hear a horn blow, team worker call out to you to be careful. You know, somebody's got their head down and texting as they're going through the work zone. Noise levels, again, passers-by, just quieter. I'm not advocating against hearing protection. I'm just making it less of a necessity. Heat, we talked about a minute ago, how that's an advantage. SSOs, for most folks here will understand what an SSO is, but for those that are not sure, SSO stands for a sanitary sewer overflow, and they're frowned upon dramatically. Municipalities, Environment Canada, EPA in the US, as well as many different places, they don't want that stuff coming down the street. Sanitary sewer overflows are never well accepted, and the consequences to municipalities can be quite costly. And then, of course, one of the advantages of doing what we're doing and talking about, the blown toilet syndrome. If we can reduce that a lot, or find ways to deal with this, we can get into that and look. I will explain in a few slides a little later on exactly how this works to your advantage if you're having issues with homeowners being troubled and upset about the issue of their home being, I guess, invaded by aliens. Okay, this is a picture of one of the test benches we use. Obviously, you saw a video earlier of the one we use in the manufacturing facility. This device here allows us to bring the test bench out to the job site and show the customers in their own world with their trucks and their equipment, what they've got, what they're doing, what different tools can do for them, and go from there. What this is a little over 9 foot long clear tube with a place on the front for the nozzle. Of course, the hose goes in. On the back end, which would be the extreme right-hand side, there's a pressure plate there which will give us a readout and let us know how much force. So if you look at the diagram, you'll see a blue electronic box there. That's a flow meter and will tell us how many gallons of water we're using. Just above it is a gray handheld monitor. That'll give us the pressure or the impact of the water jets against that pressure plate, and of course just to the right of all that is a pressure gauge, so we can look at the pressure at the nozzle and see what we're comparing to. So what we did is we took different nozzles from the marketplace. We asked the manufacturers to provide us with nozzles that were jetted at 60 gallons a minute for 2,000 psi, because we wanted everything comparable to comparable. This manufacturer actually sent us a nozzle jetted for 70 gallons, which I guess maybe might have been an advantage to them. But what we end up looking at here is we have a 70 gallon a minute nozzle, 2,000 psi at the truck, and at the end of the 600 feet of hose, I have a pressure of 1,400 psi, and I have a force on that impact plate of 13.7 pounds. Okay, so understand that plate is 9 feet away, and this is the force of the jet coming back. Tier 1 nozzles are easily recognized because they drilled orifices. The spray pattern coming out of the nozzle is usually not very well organized, and there's a fair bit of turbulence inside the nozzle. This is a 30% efficient nozzle. I come up and step up to a different nozzle now. I go to one of our competitors' nozzles, and Ann's Grenade. Very good nozzle, one of their best sellers, and personally as a competitor, I wish they didn't make it, but they do. And so I compete against it. They jetted their nozzle at 60 gallons a minute, 2,000 psi. The real flow rate that they gave us out of that nozzle, what we measured, was 58 gallons a minute. I had a pressure at the end of the nozzle of 1,650 psi. You notice how I've dropped 10 gallons a minute in the flow, but my pressure's come up by 250 psi. But more importantly, the impact at that plate 9 feet away is 75.1 pounds versus the 13.7 I had a minute ago. So that's dramatic. That's more propulsion. That's more scouring and cleaning power. That's more hill climbing abilities. And we go from there. Here we look at a high performance nozzle. This is one of our products we call the Torpedo. It's 98% efficient. Again, 60 gallon a minute configuration was the request. We ended up flowing at 57.4. Again, very comparable to the previous nozzle at 58. End pressure of 1675. We've come up 25 psi for the half gallon, and I have an impact at the end or on that plate of 97.2. That's 33% higher than the Tier 3 nozzle that we just saw a minute ago. So again, this is the same truck providing the same power. I'm getting more out of it. Okay, going to take a quick second to stop, check and see if we have any more questions.
Yes, we do have a couple more questions here. Just on a general basis, what is the frequency of cleaning pipe? I mean, I guess that's a pretty wide question, but
It's a very wide question. Yeah, how high is up and so on and so forth.
yeah.
It's all related to what the mandate is from your utility or from your environmental association, whether it's EPA or Environment Canada. It all depends on the scenario as well. If you're in an area that has excessive grease or is problematic with areas like that, you may visit more frequently. If you're just doing your run through town and everything else and do your circuit, most municipalities I deal with are either on a 4 or 5 year program to get through town, but there are areas that are problematic. Think of places where grease congregates, where all the restaurants are, where your fried chicken joints and your other restaurants, your burger places and stuff. They tend to have more grease issues and need more frequent cleaning.
Yeah, but at a high level, like municipalities every 3 or 4 years.
Yeah.
Except for notably source control areas.
Yeah, where there's a problem, then they go in and do from that. And that's one of the arguments of doing a better job cleaning is if I can get in those problem areas and make sure I get all of the debris and grease and everything else out, then I can probably extend that interval.
Yeah, it takes a clean pipe to get dirty again takes a lot longer than a half-cleaned pipe.
Exactly, yeah.
So another question that came in, and this was an interesting one, is how small can you go with your some of these cleaning units? The question was the smallest diameter pipe that can be power flushed. I'm not sure what a Renco POD type treatment plant with a mostly 1.5 and 1 inch piping.
Okay, that would depend a lot on the hose we're running in. In this case, I would run either a 1/4 inch hose. I might go to a 3/8, but I would really like the 1/4 inch for flexibility. And of course, the nozzles that would go on the 1/4 inch would be sized appropriately to go in the smaller diameter pipe. Tier 3 nozzles are available for that size and can give you some very good effects at the end of the day. There are some very good tools out there for the smaller pipes, smaller hoses.
And I imagine you just use more of a portable pressure washer type as opposed to a truck type thing.
Yeah, the 1/4 inch units tend to be 4 to 5 gallons a minute, 3 to 4,000 psi, 1/4 inch line times 3, 4, 500 feet.
Okay. Another question just came in here. How does the cleaning pressure affect an old system cracked or broken piping with these high flow pressure nozzles? Blow them apart.
The answer to your question is it's a possibility, absolutely. Every time you introduce a cleaning tool, be it saws or nozzles or anything else, you have the opportunity to cause damage if you're not careful what you're doing. I think the question is more along the lines, if I have more output from the nozzle, wait a minute, I can cause more damage to my pipe. And the reality is it's not about the output, because you can always diminish the pressure or the flow, or instead of running the nozzle at 2,000 psi, run it at 1,000, run it at 1,200. The good news is at those lower pressures, these higher efficiency nozzles will still propel quite nicely, will still move debris quite nicely, and do all the work you want to do. But the more important factor is the angles of the jets behind. The wider the angles, the more scouring I do to the walls of the pipe. And then let's take an H2S affected concrete pipe. I don't want to do that. I want to stay away from that. If I'm in an asbestos cement pipe, I don't want to do that. I want to choose a nozzle with a tighter pattern behind and have less of a scouring effect, but the ability to move the debris away.
That's good. I have another question here from myself. That access to that test nozzle performance, you mentioned that is something you can take to the field to show people. Is that something that is doable in this province? I myself and our distributor in town here, Weimar Equipment, have this equipment available, and more than happy to go and do an on-site demonstration, show you what you're currently using, what the new nozzles can do for you, as well as we're big on proving the point. If you want to challenge us, we'll go out, we'll work with your crews, bring me your worst problem, your longest, meanest hill, your most amount of grease, and let's have a go at it and show you what these tools can do. Okay, well, I'm getting a sense here from some of the conversations here that you may be called upon that. We'll make sure we get your information at the end of these things. So that's it for the questions now.
Yeah, the last slide will have all my contact information on, so. Looks like we might have one more question.
Yeah, would a Tier 3 nozzle be recommended on an ACP pipe?
Yes, but again, you need to understand what you're doing and why you're doing it. Dropping pressures is a good idea. Making sure you have a nozzle with a tighter pattern behind it, angles of incidence behind it, rather than a wider. If I have a problem where I really have to scour the walls, I want wide angles. If I have a problem, or if I have an issue where I'm concerned about the Victolic clay pipe is all cracked and damaged, the asbestos concrete is soft, and I don't want to disturb that, then you go in and you go soft and steady. Again, the better tool will get you in there. You just don't put the full power to it.
Yeah, so there's a bit of education in making those selective choices.
That's where the operator comes in. That's where he's the interface between the piece of equipment and the job.
Okay, that's it for the questions right now.
Okay, so we're going to shift here a little bit instead of talking about designs and things like that, we're going to talk about how we clean pipes. And I'll ask the question, why are we cleaning pipes the way we are, and is there a better way? And again, this is open questions. I'm more than happy to field them as they come up. If there's concerns, what I'm saying you need to have somebody talk to about, I'm more than happy to do this. So what we're going to look at here, we're going to take a quick review just to reiterate what we talked about here. We understand that as pressure loss increases as we try and move more through the hose, or the hose length is lengthened. So I've seen cases where people will take a 600-foot length of hose on their truck and add another 200 feet for different reasons, and quite often valid reasons. But when you do that, the consequence, of course, is your pressure loss will increase, because pressure loss is always rated on per linear foot or per 100 feet. If I lengthen the hose, I will end up with less pressure at the end. So again, so pressure loss, and if I can lower flow and shorten the hose, best scenario possible. We understand that pressure cleans and that the flow moves the material. The system is, for the most part, it's a gravity-fed system. Stick with the sanitary for the moment. It's a gravity-fed system, so if I can get the stuff moving and get it off the walls and get it flowing, it's going to carry downstream. Fluid horsepower, we talked about this. It may be a new thing for you to understand, but fluid horsepower is the measure of what energy I have available. It's all good to talk about, oh, look at that nozzle, makes a big pile of water, oh, it moves a lot of debris. But how much energy do I have available, and how do I put it to work is the big question. The higher the efficiency of nozzles, 30 to 60 to 80 to 98%, deliver more power at lower flows. Benefit of lower flow is fuel costs come down, maintenance costs come down, downtime will reduce, because again, I'm not driving the machine as hard. Here we're going to look at nozzles and the way we clean, and we're going to talk about this I'm going to not ask questions, because there's nobody here to answer my questions, but I'm going to make statements, and if you disagree, please make your voice heard. If you agree, hey, even more fun, make your voice heard. Okay, as technology has changed, the way we clean pipes needs to change as well. In today's world, if we look at computers, we look at audiovisual equipment, we look at nozzles, we look at the trucks we're buying, even the trucks we're buying have changed so much. Our vehicles have changed, our personal cars have changed so much. This has changed, that, and things have changed in the way we work, the way we do things. Smartphones and cell phones nowadays, everybody has one, and we couldn't dream being without it. Back up 15 years ago, and what was a smartphone? and at my age, when I started working in sales, I had a pocket full of quarters. A customer list looked like a Sears catalog, and of course nobody's going to understand what a Sears catalog is, but it looks like a Sears catalog, and I was making my sales calls out of payphones on corners. So it makes a huge difference in the way things are. So technology has changed. We need to think about, why are we continuing the way we were years ago? What's the correct speed for the nozzle to travel in the pipe, both on the upstream or going out mode, as well as the retrieval or coming back towards the truck mode? What is the best way? If you think about this and put this whole thing into the most simplest common denominator, that jetter, whether it's a small pressure washer or it's a $500,000 truck, is a pressure washer. It is nothing more than a huge pressure washer with a 1-inch hose and ability to make a whole bunch of a mess. So if we keep that in mind, and if you think about it, if you have a pressure washer and you've been out on the weekend camping with your family, you come home, your RV needs a good scrubbing and cleaning, you take out the pressure washer and you move that nozzle, that pressure washer, back and forth across that thing at 2 or 3 foot a second, you're not washing anything, you're wetting down the vehicle. If you want to scour and clean, you've got to slow it down and let that nozzle get the debris, pull it off, and go from there. And that will make the job a lot quicker. If I'm traveling in a pipe, if I'm traveling at 150 feet a minute, that's 2.5 feet per second. In a 300-foot run, it takes me 2 minutes to go from the truck to the upstream manhole. That's not unheard of. I've seen guys do it faster than that. Remember, my job one before was clean pipe. So if I can find a way of doing this and making things better, we need to think about this. And this is what I'm going to bring to you first. I am the kind of a fella that used to drive my mother nuts, and it drives my wife just as crazy. I always question things. Whether I know it as a fact, and I've been doing this the same way for 30 or 40, whatever years, I always question the status quo. So by doing that, of course, I made a few friends, and I made a few people that are frustrated with me, but that's all good. I'm still married, and I talked to her this morning. She was very happy to see me, and will be happy to see me this evening when I go home. Okay. What I call the same old, or the SOP, Standard Operating Procedure. Most operators, and I'm not saying everybody does this, but I'll describe quickly. Operators set the nozzle up, they show up at the manhole, cover comes off, nozzle he chooses his tool, he puts it on the end of the hose, he sends it down into the manhole, lines it up and gets it started into the pipe, drops the tiger tail down, goes to his truck, dials the truck up to where he wants it to be, releases the nozzle and fires it up the line as fast as it will go. That's about the way most folks do this. Again, if you're doing this, it's not that you're wrong, it's the way you were taught. Why do we do this? First things I get back from people, oh man, this is a long run. I got to get that thing going because otherwise it won't make it. Or, you know what, buddy, I haven't got enough water on this truck to worry about, going slow and doing it. I got to get it up there and get it back, and get it up there and get it back. So it's about water conservation in that case. The one I like the best is, hey, I've done this way. I've been at this job for 14 and a half years or 28 years, and I've always done it this way, and why would I change now? Well, we're going to talk about that, and maybe I can bring some light to the topic. When you clean pipe, shoot up the line quickly, and then bring back cleaning on the way back, because quite often operators will either keep the pressure at the same level as it went out, or drop the pressure down to come back and pull the debris out. When you do that, what happens is the debris that's behind the nozzle will tend to overflow the nozzle because you end up with a pile behind the nozzle and it will overflow, which is going to necessitate a requirement to go in and do multiple passes. And doing these multiple passes, of course, has its own consequence. I put this in here, and sometimes I wonder if I shouldn't take it out, but I'm going to use it here. If you had a shovel and you were asked to dig a hole, do you start digging from the top downwards, or do you dig from the bottom and dig your way out? Because when you clean the pipe by shooting up the line and then pulling the hose back and trying to clean that, it's the same thing as digging from the bottom out. You've thrown yourself under the bus and you're trying to get out. Okay? So I'm going to look at here, because one of the big comments before was water consumption. Oh man, I haven't got enough water to play games. I got to go and do this job. So here I have a nozzle traveling at 150 feet. I've got a 300-foot run. I've got a nozzle traveling at 150 feet a minute, so it's going to go out at 60 gallons a minute, which is conservative. Going to travel for 2 minutes. It's 120 gallons of water used on the way out. And on the way back, because I've dropped the pressure, it means I drop the flow, and I slow things down and clean on the way back, I'm going to burn up 5 minutes at 40 gallons or 200 gallons for a total consumption of 320 gallons and a 7-minute pass. Okay, keep that in mind. We'll get back to that. Another method to cleaning pipe is step cleaning. And while it is very effective, it has a downside. Step cleaning is very much indicated if you have very dirty lines or you have stormwater lines that are full of heavy debris and stuff like that there. It's like working and excavating a basement for a house or a pool in your backyard. You don't go in and take it out in one big bite. You take it out shovel load by shovel load. This is what step cleaning does. It's one shovel load at a time. You bring the material back, you bring it out of the pipe. You go in, you get some more, bring it back, get it out of the pipe. This is step cleaning. It is very effective on cleaning larger diameter and pipes with some heavy soil in them. What the problem with the step cleaning is, it requires cleaning the same length of pipe many, many times. Here I'm cleaning a 300-foot run. I'm running in 50-foot steps. Because I go into 50 and then 100, then 150, then 200, I end up running a total of 1,050 linear feet to get 300 feet in the books. And that first section of 50 feet gets cleaned 6 times. So it makes you wonder from a time and efficiency point of view, is this the right thing? And I'm telling you, there are times when this is absolutely the only way to clean pipe. Stormwaters, heavy debris, that kind of stuff, this is the way to do it. But if I have a better way, like this case, I end up cleaning 3.5 times the length of pipe I get credit for. If my contractor, well, if I'm a municipality and the boss is saying, hey, you got to give me 3,000 feet in the end of the day, man, I need a lot more than 3,000 feet doing this. Okay, let's talk about Tier 3 nozzles. This is where I'm going to bring something novel and hopefully of some interest to the group. With Tier 3 or higher efficiency nozzles, I can change the way I clean. You saw earlier how I can drop the flows, drop the pressures, and still provide all the cleaning power I want. So if I go and change the way I clean, I want to, instead of having that nozzle shoot up the line, and in essence, the only thing I accomplish by having the nozzle travel at a high rate of speed is I get the nozzle from the truck to the upstream manhole. And I've wasted, in this case, was 120 gallons of water just to do that. What I want to do is slow the nozzle down on the way out. I want to go from a running speed to a walking speed, and I want the nozzle to spend more time in the pipe cleaning on the way up. This will clean the debris and the grease and the whatever's stuck to the wall of the pipe, pull it off, and get it moving. Now, the water that I've added to the pipe will help that stuff travel. So the water will act as a conveyor belt and will carry the fecal matter, will carry the organics, will carry everything else down towards the extraction point or where the truck is. What it won't do is when I get into the heavier cleaning of the stones and rocks and things like that, they will tend to want to fall out. But I've gotten rid of most of the debris here. When I come downstream, so I go upstream, and when I go upstream, I run pressures somewhere around 1,200 to 1,400 PSI, maybe a little less, maybe a little more, depending on conditions, but I don't always run the truck at its max. When I come back and start cleaning on the way back, so I get a pass going up cleaning, and when I come back, I drop the pressure down to well under 1,000, and I collect all the debris, the rocks, and everything else on the way out. I end up getting 2 passes for the price of 1, number 1, and I get the job done in a single pass, 99 times out of 100. Typically in sanitary. If I'm in stormwater, things change. Stormwater becomes more of a step cleaning process. But in sanitary or in areas where I can get away with this works extraordinarily well. 1 pass and I'm done. So I go back and I look at my comparisons. Left-hand side, I saw it took me 320 gallons in 7 minutes to do 1 pass. On the other side, because I slowed it down, I've taken 5 minutes to go upstream, but because I'm using a higher efficiency nozzle, and I'm burning 40 gallons a minute, I'm only going to use up 200 gallons on the outward length. Now, when I come back, I'm going to travel back at the same speed, but because I drop my pressure, my flow drops down to around 30 gallons. If I'm down to that level, my total consumption for the segment of pipe is 350 gallons versus 320. My time is 10 minutes for that pass versus 7 minutes for the other pass. But the trick here is I do it in 1 pass and I move on to the next section. If I have to go back in and do a second pass at 320 gallons in 7 minutes, now I'm wasting time and money. I increase my productivity because I can get more sections of pipe done with a tank of water. My blown toilet issue becomes almost non-existent. It's coming up very soon in about 2 slides, maybe 3. The hose is exposed to 1 pass. It goes out once and comes back once, which means that every time that hose goes out in the old style, or the other way of doing it, means every time it goes out, that hose is subject to damage. It can get hooked up, it can get hung, you can get stuck in pipes. All that stuff happens. The more often I go in the pipe, the more opportunity I have to have issues. The hose is retrieved through a clean pipe. If I run the old system where I shoot up the line and clean on the way back, that hose is coming back through everything I'm trying to remove. And that stuff comes up on the hose and sits on the hose reel and drips. And then at the end of the day, it goes back in the shop, back in the garage, and the next day things start to smell a little. Okay. That unpleasant what I call the unhealthy misting. If you've been an operator working around a manhole, as you bring that nozzle back and you get within the last 50, 60, 70 feet, and you get that big blast of warm, moist air carrying all kinds of wonderful things in it, you take your glasses off afterwards and clean your glasses and wipe your face, okay? That stuff is not good stuff. And if we can reduce that, we can find a way to take care of it. Number one, the nozzle's coming back through a pipe that's already cleaned. And number two, I'm running at a much lower pressure, so I don't get that misting. You saw earlier in the video how the high efficiency nozzle kept a clean stream of water and like a laser beam type stream of water versus one that opened up and fanned out. All those droplets of water that are fanning out of that nozzle now become airborne and are carrying all that unpleasantness up to the operator. The work environment is healthier, just for the reasons I've just stated. Another important factor from a safety point of view, we always talk to folks about being careful that nozzles don't get turned around in the pipe or end up going up a service. We put a skid or some kind of an assembly behind it to lengthen it out for safety reasons, and I agree with that entirely. I have thoughts a little different, but that's not this point of discussion. But if the nozzle travels out at a high rate of speed and hits an object, be it a rock, a wall or something, and then deflects and goes up a service, now you've got trouble. If the nozzle hits the end of the pipe, bounces and comes right back inside the pipe, and now it's coming down all full steam ahead back towards the operator, now we have problems. If the nozzle is slowed down, instead of driving it down at a high rate of speed, but you walk it down the pipe, there's almost no chance for that nozzle to get deviated. Blown toilet syndrome, folks. This is the one that raises a lot of questions, and I'm going to invite the questions to come in because it's really good. When your homeowner comes out of the house, walks up to your crew, and they describe what just happened in their house, this is the picture they paint. Okay? You blew up my toilet. You caused a problem. And, you know, from a homeowner's point of view, they're not wrong. What makes this happen? What is the major contributing factor to this issue? And you notice how I said that, major contributing factor. There is no one cause, but there's one cause that is predominantly the issue, and it deals with airflow. So if you think about the airflow that's in the nozzle, if you're a truck operator and you're running and your helper's with you and you put the nozzle in the line and send it up the line, and you send your buddy up there and he hasn't released or removed the cover and he has to try and pull it off with the nozzle in there, you have a feel for how much vacuum, how much air is being brought in there and going on. So what happens is that air is in front of the nozzle. And I'll use this for an example really quickly. If I have an 8-inch pipe, okay, coming towards the nozzle, I have an 8-inch column of air. And if you've never had the experience, when you see our test bench we had earlier, I invite people to put their hand in front of the nozzle and feel just how much air is there. And it is literally shocking how much air is traveling. So I have a high volume of air traveling at speed coming down the pipe, an 8-inch pipe, it gets to the nozzle. And once it crosses the nozzle, because I have a hose behind, a 1-inch diameter hose, and I have all the added water that I've just added through the nozzle, my 8-inch pipe will now become likely a 7-inch pipe. And using the old cleaning method, what I call the same old, is I have an issue on the back end is that I have that pile of debris that's behind the nozzle. So the air travels over the nozzle, 8-inch pipe, reduced to a 7 because of the water in the hose, and at the distance behind the nozzle I have the debris, what I'm trying to get out of the pipe. That debris will shrink the pipe down to 6-inch, 5-inch, or heaven forbid down to a 4. So I'm trying to shove an 8-inch column of air through a 5 or a 4-inch orifice, which means that I compress the air between the nozzle and the debris. And once that debris goes by the service, Mrs. Brown's house, Mrs. Brown gets an unpleasant surprise because she provides me with a service line that is just basically a relief line, and it just blasts the air straight up that line. If the home is not properly or adequately ventilated, or there's an issue because there's something that's been blocked or whatever else, then the venting happens through the toilets and the floor drains. And this is where the majority, I'm talking 80 or so % of the blown toilets happen for this reason. There are other reasons as well, but some of those you just can't control. It's just a connection issue or whatever else. Now, who's to blame? If you ask the homeowner, it's really simple. You look out the window, there's that guy with that big truck making all that noise. He's the guy with the coveralls on. He's the guy that causes my problem. But the city has a mandate and a necessity to go and clean these pipes. So how do we get both things satisfied? How do we make this happen? What can we do to reduce the chances. You notice I'm not bringing a solution, this will fix the problem. I'm helping you to reduce the incidences. First answer that I always get back when I ask this of a group is, oh, we reduce the flow and pressure. Take the pressure off the nozzle and use a nozzle that's a low flow and it goes in there and we don't blow toilets anymore. Well, congratulations, that is a fix. The downside is if you're running at least a lesser efficient nozzle, then your cleaning capacity, your cleaning power out of that nozzle is reduced. If you reduce your flow and pressure on that nozzle, you may not be cleaning the pipe as well as you could if you had a better nozzle. So reducing flow and pressure is an excellent answer. It's just, you got to stop and think about what tool will I use when I do this. The next answer, remember we talked about how the air crosses the nozzle and then compresses behind the nozzle? What if I could find a way to not let the air cross the nozzle? You know, and the answer is that exists. This nozzle we call the equalizer, and it's designed, look at the terminology, to virtually eliminate blown toilets. So again, 80% of the time it's an air volume issue, and if it's an air volume issue, this is the nozzle that will fix that problem hands down. The downside to this nozzle, it's all of $5,000, and it uses a lot of water. There's 18 jets on this thing. Okay? Now, does it work? Yes. And if the problem is big enough, then you know what? That might be a heck of an answer. But before we go spending $5,000, let's look at the third option. Let's remove the material from behind the nozzle. If you stop and think about, I don't know, 10 or so slides back, I was telling you to clean slowly on the way up, get the debris into the water stream, let the water stream carry it away. And then when you come back through the nozzle at A, reduced pressure and flows. But the more important thing is that debris that you're trying to get out of the pipe is already gone. And the restriction of the pipe behind the nozzle, if you remember how it turned from 8 to 7 and then into a 654 behind it, now that pipe is pretty much all there to handle the airflow. If I can't compress the air, and the air has a place to go, then I don't have an issue with blowing toilets. I'll do this last slide, and if there's a question or two, we'll deal with these. I was invited by the City of Ottawa in Ontario. They phoned me up one day, and this has got to be 2.5 years ago or longer. They phoned me up one day. The guy's name was Scott LaBerge. Remember, just like it was yesterday. And Scott says, Ken, you don't know me, I don't know you, but I heard you're the guy that can help us out, and boy, do we have a problem. There was some areas of town that the blowing of toilets was so bad, City Council had banned them from cleaning the pipe until they could deal with it, until they could find an answer. And if you got pipes that are that bad, you need to clean them. That's all there is to it. So he phoned me up and he explained his issues, and I gave him some thoughts as to what I thought were some of his issues, and as well as some remedies. He then invited me. He said, Ken, when can you come? And we set up a time, and I went out there, and I did some training with his operators, his supervisory staff. I even had some contractors who worked for the city that came in and listened to the class. Basically, what you're seeing today is very much what they got, as well as a demonstration. There's that clear tube in the back of the pickup truck working again. And what we ended up doing for the City of Ottawa is we talked to them about changing their methodology, using Tier 3s, reducing the speed, dropping the pressures and flows, and we reduced the incidence of blowing toilets by 88%. They were thrilled. The cost to them was a little over $1,200 to $1,400 a nozzle, and it's just a regular cleaning nozzle, lean and mean on water, and just does a heck of a thing for them. We talked earlier about angles of jets. This talks real quickly about it. The wider the angle, 30, 35, more cleaning and scouring, less thrust. The tighter the degrees, 10 degrees or in that area, very good thrust, but not so much cleaning and scouring. If I have a pipe that I'm concerned about the condition, I want the tighter angles. If I have a pipe with heavy grease and it's a PVC or it's a clay pipe in real good condition, or it's along those lines, then I want the wider angles. I want to go pull that stuff off the wall of the pipe. Do we have questions based on?
I think we do have a couple questions. I'm not sure
Okay.
exactly how. First one up was nozzle setups for a typical pressure washer, and do any nozzles rotate?
The answer to your question is yes, I know how to do that. Typical pressure washers, typically 2, 3, 4 gallons, and we can do that quite well. Big question I have is, what are you trying to clean? Because you need power to get it done. So I've had fellas wanting to clean a 24-inch culvert with a pressure washer, and it's just like, guys, you're not going to get there. It's not going to happen. Okay. What was the second part of the question?
Nozzles that rotate.
Yeah, nozzles rotate all day long. We have lots of those, and many manufacturers build those. Yeah.
Okay. The next question was, I think it was close to what you were talking about, the distance to a resident's main line, and how does this affect a sewer line backflow preventer? I'm not even sure.
Well, a backflow preventer, I'm thinking more like a check valve or a clappet valve inside the sewer, I think is what they're asking about, and it would be there to help alleviate this issue of blown toilets, because as the pressure comes back up the line, it slams that shut and doesn't allow the pressure up. If you've got cleanouts, quite often in this scenario, I've seen the cleanout covers pop off and they go sailing quite high. But the proximity of the house, the angle of the grade, that all plays into the factor. But it's the air volume. If I can reduce the air volume, if I give the air a place to go other than up the service, the problem pretty much goes away.
That makes sense. So a lot of it's thinking before you start the job.
Well, it's cause and effect. What am I doing, and what can I change to make it different?
Yeah, the service check valves is a reference that Dixon gave us. Yeah. I was just looking at that last slide you showed on the angles, and there was a question earlier about struvite.
Yes.
A particular hard material like that, you would go with which one of those?
You would go with a wider angle. We have different nozzles. I'm thinking of one in particular is 25 and 40 degrees, so very, very wide angle. It will go and pull the material off. While that does a good job, what I would look at as opposed to that kind of a nozzle would be a nozzle with a controlled rotation head, and that would clean full 360 and not leave stripes and stuff inside the pipe. It will basically hone and clean the inside of the pipe up quite nicely, versus a nozzle that will go through and just pull off where the water jet hits. But between the water jets, you'll end up with some what I call stripes inside the pipe. Right. So again, and it could be a two-pronged attack. I could go in with the regular nozzle, get most of the stuff out, then go in and polish and finish up with the other nozzle, and then I'm out of here. Again, like we said earlier, any debris left behind, be it struvite or grease or anything else, is the beginning of your next blockage. So if you can get it gone, that will extend your cleaning periods.
Yeah, that makes sense.
Okay, we'll go forward here because we're going to run into a bit of a crunch on time, but that's all good. The important part is all done. Now we're going to look at some interesting things here. Oh, I'm like a bit of comedy. Here we have Harry believing that he's got the right tool and the wrong job, but he'll make that nail go in. And we've all done things like that. I mean, I know I have as well. Oh, going the wrong way. And then, of course, we'll call him Bob. Bob's got the right tool, but he's going to be there for a while and see what's up. So it's a question of using the right tool, using it properly, and getting the job done. So I've talked a lot about taking Tier 3 nozzles, reducing flows and pressures, jetting these things lean and mean to save water. And you know what? 80–90% of the time, it's a great answer. But there comes times when you just need that more flow, because I've got this long hill to get up and over. I've got this really long pull, or I've got this or that. And quite often what I find is people jet their nozzles to the worst scenario they have to face. But then when they're running in the everyday stuff, they're just too much water, too much everything happening in the nozzle. Running them lean and mean makes a lot of sense, but then what do I do when I need that water, when I need a nozzle that's going to give me another 15, 20 or so gallons of flow? This is where this comes in. We call it a turbo booster. It actually threads into the back of the nozzle, adds 3 jets back there. Depending how I configure it, I can add 15, 16, 17 gallons of more water. So when I need that extra flow to help carry material, because before we talked about pressure, scours, and cleans, flow carries material. When I need that extra flow, I just screw this in the back of the nozzle, do the job I have to do, take it off, put it back in the toolbox, and go back to the lean and mean nozzle. Here's a nozzle that's designed for removing heavy materials. We talked about struvite a little bit ago. This is an answer that we can use. And if you'll see here, I've got a pipe. You notice how I mark here in red in very big letters, do not use in clay pipe. That also applies to asbestos concrete and badly damaged pipe, because this nozzle, when it runs, vibrates, jumps up and down, shakes and rattles and rolls, and it is meant to remove those hard deposits. If I have a clay pipe in there, you can believe I will be cracking, breaking, and damaging the pipe. I had a fellow look at this nozzle and, hey, I love this nozzle. I also sell pipe. He does pipe replacement and lining jobs. He said, I can use that nozzle and make more money. And I said, well, that's not quite ethical, but anyhow. But you see the way this thing works. As it spins, it is on the interior barrel. Back this up just a little bit. The barrel there, the silver barrel, is actually offset like a cam on your car. And as it spins, it starts to cause this thing to jump and vibrate. You notice on the brown parts, they got those nodules on there. They're there for a reason. So when this thing bounces and vibrates, that energy is sent through that nodule and has more impact. Oop, going backwards still. So here's that video. That video there we saw what it did. Going to get out. We're going to talk about large diameter and stormwater. You know, we talked about step cleaning and things before. This is where these nozzles come into. These nozzles have all the water coming out the back of the nozzle and directed towards the floor or the bottom of the pipe. We call them floor cleaners. They're called bottom cleaners. They're called sleds or boats. There's all kinds of different names for them. But the idea is that they can be used to move heavy debris in stormwaters and larger diameter pipe. They can be used as singles, as you can see on the left-hand side, or you can use them as a double, twin them up into two, and I can clean an 8-foot wide flat bottom culvert with this combination with an 80-gallon a minute truck all day long and move material like it was meant to be. Here's a video of the floor cleaner being used in Alaska. I was up in Anchorage just recently, and they wanted to see a demonstration of this thing. How much debris could this thing work? This was a compacted parking lot that had been driven over for years, kind of like a hard pack soil. And we just ran this thing, kicked it into gear, and of course they did the slow-mo in the video. I thought was kind of nice. And you can see how this thing, all the water, all the power out the back and downwards, and it does the scouring, it does the cleaning. You can see the clumps of dirt coming out and all of that stuff going on. So this works extraordinarily well for what we want to do. The downside to this nozzle is that all the jets come out the back. So the nozzle itself has to climb on top of the pile and then start to pull the material back once it's up on top of the pile, which sometimes is not so easy. You can have a 2 or 3 foot wall of debris to get up on top of. Or if there's no clearance in the top of the pipe, if it's a 24-inch pipe and it's got 20 inches of debris, there's no clearance for this nozzle. So now we got a problem. How do we deal with this? And the answer would be what we call the OMG nozzle. It's for stormwater, corrugated metal pipe, and large diameter, fully obstructed. It also works extremely well in pipes that you don't want to attack the walls. Think of the asbestos concrete, brick-lined ovals. Quite often you get the dual-purpose storm and sanitary all in one in some of the older towns. And that brick, they don't want to disturb the brick. They don't want to disturb the mortar. So that's where this comes on. This is a 36-inch pipe. If you look to the left side of the picture, you'll see there's a latch on there as well as a big strap. There's some latches and there's a door that opens. We filled that thing up with rocks and debris and clay and dirt. This was shot in Las Vegas, Nevada. Yeah, I had a lot of fun in Vegas that trip, and we got into it. So what I want to show you here, the video will start. Look at the stream of water coming out the back of that nozzle. It's straight out the back. So it doesn't go to the floor, it's straight out the back. The reason it goes straight out the back is because it is designed to work in corrugated metal that has got a rotted bottom or in pipes that have issues that way, and it just shoots the water straight out the back. It's got a forward jet, so again, this one doesn't have to climb on top. With the forward jet, it will dig into the pile and go. Watch the debris come back. When I set this demonstration up, the operator had backed his truck away some 100 feet, and he hadn't put up the bales of hay. I strongly recommended we do something, and we did. He wasn't in agreement, but we did it. And lo and behold, after the demonstration, he came to me and said, "Wow, I'm glad I did that." Okay. Well, you'll see now what's going to happen. The debris is pretty much out of the pipe. The hose is going to come back. You'll see the leader hose show up in a second. They'll shut down, and I'll walk up on it. You can see how much debris. Keep in mind there was sand and dirt and clay and stuff in here, as well as all this rock. Most of that stuff washed away, and it's out of the pipe, but it's washed away. But you'll see the amount of rock that's sitting here. It's like waiting for water to boil, right? There's the leader hose coming back in. And we'll shut down here in a second. That's the rocks we just brought out of there, folks. Okay. When it comes to chain flails, root cutters, and things like that, we can provide you with chain flails and root cutters to go from 2-inch pipe all the way through to 48 and beyond. This 48-inch configuration, this nozzle here in front of you, is configurable from 6-inch through 48-inch and can go up to, I've had it as big as 10 feet in some instances. You can turn that into cutting minerals. You can cut roots, protruding surfaces. Anything you have to have happen can happen from here. Quick video on this one here is a 24-inch pipe with a 6-inch taproot coming in the middle. This video is a tad lengthy, but it's here for a purpose. We can look at this. This is a solid taproot coming in from the top of the pipe. Concrete pipe, and we're going to see the cutter come up. The camera's here. The camera's going to control. Speaking of which, never recommend doing any kind of root cutting or anything else unless you've inspected the line just previously, and working with a camera in the line is much better. So what I want you to see here is this is a high-speed, high-torque cutter. It will barely slow down as it starts to eat into these roots. You can see the center nose cone or the auger on the front end is starting to come through. I want you to watch that center auger, and as this thing makes contact, it's not quite yet, you'll see a big chunk of stuff come off the bottom here in a second. But look at the speed at which that thing is spinning and turning. Now the camera guy pulls him back a little bit. He does a quick inspection, and we're going to fade in and fade back out. He'll come back in, and this is where I want you to watch that center spinning point that's trying to poke its way through this root mass. And I just want to highlight, when you see it, it will pull very much to the right, and that's the torque that this cutter has. Unlike most cutters on the marketplace, they don't have this kind of torque, and that means that basically they stall out. You run into a root mass, they stall out. You run into a root mass, they stall. You run into something that's difficult, it stalls out. This tool barely changes speed. You can hear a slight shift in noise, but it goes from there. And you can see now, as it comes back in again, he's going to hit the root mass. At the very end, you can have a look-see. One of the big problems that people have with chain flails and root cutters, they fear that they're going to damage their pipe. If you look at our root cutters, they all have 5 skids on them, and the 5 skids are there for a reason. Because we have so much torque, it's very imperative this thing stays centered in the pipe. It can't be allowed to wander. And that's where people get into problems with chain cutters and pipe. See this thing go? People get into problems with chain cutters because they undersize them. And this is a 24-inch pipe. If this is configured correctly, it's going to be 23 inches and change. And it's got very little wiggle room, which means that the tool can't get turned around. If I ran this as a 16 or an 18-inch in this 24-inch pipe, it'll be all over the pipe, bouncing around inside, damage the pipe, and break the tool. And now, if I remember correctly, this video will show us a chance to look at the wall of the pipe where the cutting has happened. Yeah, here it is. There's literally no damage to the pipe. Again, because the tool is set up properly and used appropriately. If you don't set up the tool properly, if you use it inappropriately, you're going to have issues. Another video that I'm going to skip over because we're going to run into our but hard deposits, concretes, minerals. This thing will work. Here's the tool that I wanted to talk about, Struvite. Okay. Now, you notice I've got 2 different tools on the marketplace. The one on the left is a KEG product we call the Aqua Power Clean. The one on the right is called the Warthog, and I'm sure most folks listening in would know what a Warthog is. Warthog makes a bunch of different levels of tools. They got their WG1 or their Classic, which was many years ago. They built this thing. They still build it because it's very price competitive. And then they have new things out called the Switcher, and there's a Root Destroyer and other nozzles out there which work quite well. I like to give credit where credit's due, and my local distributor here in British Columbia, Weimar, sells both products. And will sell the right tool based on the application. But what they are is controlled rotation heads. So the head doesn't spin freely. We control the speed of rotation. So what we're going to do here, this is a view. I can cut roots typically the size of a man's thumb. That's my hand, that's my thumb, and you can see the root that's there. It's typically the size of a thumb. It'll cut right through them quite quickly. Here's that clear tube assembly. You've got the flow meters and pressure gauges. And we'll let this thing do its thing. You can see for yourselves. We're going to introduce the root, or the 2x2 inside, and show what this thing can do. Again, remember, controlled rotation head. This nozzle turns at 600 RPM, regardless of the pressure you put behind it. We use a centrifugal clutch inside and a braking system inside the nozzle that basically requires zero maintenance. There's no oil changes or anything else to do this thing, other than wiping down the nozzle when you're finished and making sure the water jets are unobstructed. There's no maintenance on this nozzle. Want to just highlight too, while we're waiting on this, he's going to run this for 60 seconds in there and we'll see what it'll do. But I want to highlight that all of these demonstrations, all of this stuff is all doable at your site. We even, if a customer's interested and wants to take this on an extended trial, we're happy to do things like that, and because we believe the tools, once the customer has them, realizes quite quickly just how effective they can be. So remember, this is a piece of 2x2 kiln drying. It's not like a root, but it's like a root in some degree. So, struvite, mineral deposits, grease, roots, it's all good. And that's what that nozzle does in 60 seconds.
This
Okay.
is how much it cut in exactly 1 minute. As you can tell, it's going to handle roots, grease, probably mineral deposits pretty good.
Now, the one thing about this, when it deals with grease, if it's a soft, that soft, stinky grease that we have to deal with, it actually emulsifies it with the water, and it looks like porridge going by the truck. It just goes straight by the truck and goes out. It doesn't come out in big chunks and blocks and everything else. We're getting near the end of this, and timing's going to be just about dead on. This is a camera built into a nozzle, or a nozzle built into a camera. Call it whichever way you want. High definition, self-leveling head, 80 LEDs in the front end, 98% efficient nozzle on the back end. It records as it cleans, and you can see the pipe pre-cleaning and after the cleaning assessment. Basically, your jetter hose becomes your...
I'd like to talk today about
here's my buddy Dan. We're going to get through this. Dan Story is our sales manager. He's a good friend of mine, and my wife thinks he's my brother from another mother. But
16-inch pipe with the possibilities
your crews can do the assessments. You can do all kinds of stuff. We have an app for this. We have we can send it up to the cloud, the video from the street up to the cloud, and then send it off to your supervisor, your homeowner, whoever needs to see what's going on.
It's very simple.
We can talk about how it operates. We'll see that in a little bit. Here's a video I took in, back up. Why does that video not want to play? Okay, doesn't matter. This was done in 2014, so these things have been around for 6-7 years. This is Edmonton, Alberta in the end of January. There was ice and snow everywhere. We had to use a metal detector to find the manhole, and we ran the nozzle in there, and we ran across root masses, we ran across protruding surfaces. Everything was there. We saw it all with the camera. We threw the cutter in there immediately following. Problem was dealt with. We moved on to the next issue. Going over and just doing a quick review. You can clean your wastewater and storm lines better was one of the goals that I wanted to talk to you folks about, and hopefully I've managed to do that today. I've talked to you about savings in fuel. We say 9 to 17%. I know I can do that. The 9%, hands down, eyes closed. I've actually worked with a contractor in Montreal, and he's saving on average in his trucks between 15 and 20 liters of fuel every day based on what he used to do, and his productivity has increased between 10 and 15%. Man hours, machine hours go down for cleaning lines. Wear and tear goes down for all the reasons we spoke about. And here we talk about conserving water to clean lines. Lowest long-term cost. Yes, you will spend money for the tools, but if we can't show you, and this is one of the things we do quite well, if we can't show you where these nozzles will pay for themselves, then we're suggesting to you not to buy them and shop somewhere else. But if our tools can do as we say, they can be a big asset to your utility or your company. Clean pipes, job number one. If we're not doing that job, there's no reason to come to work in the morning. That concludes my presentation. You can see my contact information on there, phone numbers, emails. And of course, back through the EOCP would be able to get you in touch with me too if need be. If anybody wants a copy of this presentation, I don't know, Heather, will you folks have it available, or should I? Okay, perfect. So we can get it in many different places, folks. Again, thanks for everything. Are there any more questions?
Yeah, there's a couple more questions. We've got one here. Are there efficiency charts that come with the nozzles that would include information including like pipe type, diameter, elevation, gain, and loss to give best running efficiencies?
Not so much a chart and anything else. The way I address these concerns, I listen to what the customer's concerns, what their issues are, and then I will recommend how the nozzle is to be set up or configured for the specific job, and go from there. Again, I'm a big fan of fewer tools than more tools, but you need the tools you need to get the job done. So happy to provide any and all tools that people need, but at the end of the day, my job is not loading up your toolboxes. My job is giving you the tools to do the job. So to answer your question, is there a chart? No. Can I assist and help in getting that done, depending on what your goals are, whether it's saving water, increasing productivity, getting better work, more productivity out of your day and things like that, or if you're working on the cruise and you just want to go home a little cleaner and not quite so worn out and tired, we can show you how to do it.
Okay. There's another one just popped up here. It is advised to you, or I guess it's a question. Is it ever advised to use the truck vac downstream of the manhole to create a negative pressure to assist in airflow, i.e. avoid blowing toilets? Most trucks are moving 4,000 to 7,000 CFM.
Yeah, the trucks do move a fair amount of air. If you put that in downstream, I'm here. The way I heard the question is downstream from the hole you're working in. So that is, in effect, it's going to increase the airflow moving down through the pipe. So I think that's going to be have a negative look and see what's there. There's also a thought in the industry that when you open the upstream manhole, you alleviate the problem of blowing toilets. And actually, the reverse is true, because when you open the upstream manhole, you allow easier access for the air into the system. And when you've got more air or easier access for the air to come through, you can actually increase the opportunity to blow toilets. I'm not saying don't open the upstream manhole, because the advantage of opening the upstream manhole is I'm not going to take the air from the homes. The P-traps and all that stuff in the homes will not be drained. But if you open the upstream manhole, then be aware of what you're doing. Again, we go back to lowering flows and pressures. We talk about slowing the speed of the nozzle down to clean on the way up. Take the debris out of the pipe so that when I come back towards the truck, the air has a place to travel to.
I don't know if you recall, further back there was a demo, and there was a question that came in on what was the PSI on that demo.
There were quite a few demos.
I know, it was the first one that you, the first video.
The two nozzles side by side? I think that's the one they're referring to.
I think so too.
If that's the one, I don't know the pressure, but I'm assuming that the pressure was taken up to beyond 2,000, more likely 2,500, because we test the nozzles to their maximum. All our products are rated for 4,000 PSI, but made to work in 2,500 to 3,000 PSI.
Yeah, it is the biggest one. Yeah.
Okay.
Okay. We're running out of time, so
we're within 10 minutes of the goal. So.
Yeah. Okay. Is there any other? There's nothing else. We're open. I would like to thank you very much. That was surprising how much information that you pumped out there, and I think judging by the comments back, there's a few people that enjoyed that presentation.
I would invite anybody that wants more information or would like to see firsthand for yourselves, happy to do it for you. We can get that set up and get it done short term rather than long term.
I'm sure there's a couple of people writing that number down as we speak.
Okay.
So.
Okay, and again, EOCP was happy to provide my information should you need to get hold of me.
Yep. Okay.
Okay.
So yeah, thank you.
Thank you, folks. Thank you so much.
I'd like to remind people about the survey to get that filled out for everybody, and we're going to take a 15-minute break, and I think we're back at 3 o'clock. So we'll see you at 3 o'clock.